Work is an exchange of energy, and we can tell how much work is being done by looking at the force dotted with the distance that something travels. In general, the force is going to change, and the distance that we travel will not necessarily be a straight line. So if we start at point A, designated by a vector, and we go through to some point B, let's make those just a little bigger, making them a little easier to read. Along our path, going from A to B, we have a little tiny infinitesimal distance that we're going to travel, dl. The work done as our particle, our rigid body or our point particle, goes from here to here, it's going to experience some force. And the little tiny bit of work that is done is going to wind up being dw is going to be the dot product between these two. That means if we're going all the way from A to B, we can say that the work done is the integral from A to B of force dotted with dl. Note that we are going along some line. This line isn't necessarily straight, and what we can say is that because we're going along some line, this integral has a special name, and that integral is called a line integral. What we're going to do in this video is we're going to actually do an example of a line integral where we are taking the work of this particular force that we've got written on our slide there, going from the point that we're starting with to the point that we're ending with. Note that we're going along the bottom, along the x-axis, then we're going to go straight up, and then we're going to go back a little bit. And that path is going to be the path that our particle takes, and we're going to look for the work done on that path, along that path, on our particle. The first part of that path is the bit along the x-axis, and because we are going along the x-axis, that means we're going from the point 0, 0, out to the point 3, 0. So this is going to be our first limits of integration, and the particular dl that we're going along is going to be in the x direction. So we've got a dx x hat for our dl. This means that our work is going to wind up being the integral from 0, 0, up to 0, 3 of our force, which we know is 3x squared y x hat plus 2y y hat dotted with dx x hat. Of course, because it's a dot product, this is going to go to 0. We're just left with the x hat dotted with the x hat. That gives us 1. So we're left with the integral from 0, 0 up to 0, 3 of 3x squared y dx. Oops, I got my limits backwards here. This is actually 3, 0, not 0, 3. And that's really important because what's going to happen is all the way through, y is going to equal 0. And because y is going to equal 0 all the way through, this entire line integral, or this entire portion of our line integral, is just 0 because y is equal to 0. Our next piece is the piece that goes up. And that piece that goes up goes from 3, 0 up to 3, 2. And because we're going straight up, our dl is actually going to be in the y hat direction. Because it's pointing in the y hat direction, we're once again going to take this dot product, but this time, only this term is going to wind up surviving. So we're going to go from 0, we're going to go from 3, 0 up to 3, 2. And then what we're going to have is this same thing, but it's going to be dy y hat. And that's going to leave us with 2y dy. And of course, the integral of 2y dy is y squared, evaluated from 0 to 2. So that is going to be 4. So the first part was 0, the second part is 4. We've gone along the bottom, we've gone up, and now we have to do that bit that goes back. That bit that goes back is going from 3 to back to 2. What might be a little counterintuitive is because our x is actually getting smaller, our dl vector is still going to point in the positive x direction because the negative is being taken care of by our limits of integration. So we've defined a positive direction and our dx has to be pointing in that positive direction. Because it's doing that, our limits of integration wind up going in the direction that they do. So we are integrating from 3 to up to 2. And our dl, as I said, is going to wind up being exactly what we had in the first place, dx x hat. Which means that when we take this dot product, we're going to wind up with the same integrand we had before. 3x squared y dx. But here, y equaled 0, so this entire term went to 0. This time, y is going to equal 2. And because y equals 2, we can say that this is equal to 6x squared dx, which is going to be 2x cubed, evaluated from 3 to 2. And because it's evaluated from 3 to 2, we put in 2 cubed times 2 is, of course, 16, minus 3 cubed, which is 27, times 2, which is 54. And 16 minus 54 is negative 38. When we integrated, we saw the first was 0, and the second piece was 4, and the third piece was minus 38. Our work along the entire path is going to be equal to 0 plus 4 minus 38. So the work is equal to minus 34. What this video showed was that the line integral for work, or any line integral in general, can be broken into these various pieces. Along each of those various pieces, we have different DLs. Sometimes they're pointing in the x direction, sometimes they're pointing in the y direction, and we'll see in a different video, sometimes they're pointing in a combination of both, and you have to actually create a more complicated mathematical expression. A picture can often clarify the variable's values, like the fact that y was equal to 0 here, and x was equal to 3 here, and y was equal to 2 down here. A picture can really help with that. Tune in for our next video on line integrals depend on path.